Hi, good morning and good afternoon. My name is Ilana Rennert. I help manage outbound marketing here at Western Digital. And today we are joined by Clay Ryder in our data center systems marketing group to talk about object-based storage and why it matters to your data. We will have time at the end of the presentation to answer any of your questions, so please don't be shy and submit them at any point. But I will now go ahead and pass the mic over to Clay.
And thank you for joining our webinar, Know Thy Storage, Object-Based Storage. I'm Clay Ryder, part of the Data Center Systems Marketing Group at Western Digital. Today we're going to discuss a variety of topics related to object storage. We'll cover what object storage is, and more importantly, why do we need it, and why does the data center find value in it. We're going to discuss supporting data at scale. We'll examine some of the limitations of current RAID technology and file systems to see why we need a fundamentally different approach to supporting data at scale. We'll take a look at how object storage delivers space-efficient data protection and resiliency, and we'll also look at some example use cases where object storage is making a difference in data centers around the world. At first, we need to realize that we're facing a rapidly changing data center and a very different world of storage. We're moving beyond data in the data center traditional sense. No longer do we have a glass room with a mainframe system and a terminal associated to it, or for that matter, even client server. We've moved into a world where data has shifted dramatically. No longer is it tied up in the data center alone, separate from data we use in life. But we actually interact with the data center far beyond the physical confines of the data center. We do that through the cloud, we do it through the ubiquitous smartphones or other handheld devices that people have. We have a planet with billions of people, with billions of phones that will be running millions of different apps, and the result is we are connected through a cloud in ways that didn't exist formerly. Mobile devices have changed the way we communicate, not only with friends and family, but with our workplace and commercial interests as well. Devices across all of the industry generate data, from microscopes to manufacturing robots and pressure sensors, as well as our personal and commercial bank accounts and photos and music downloads and social networking. When you look at this exponential growth in data across billions of people, you see the challenge of storing that data has become paramount, and more importantly, to make good use of that data. What end users need for this ocean of data is simplicity. You need access to the data you want, when you want it, and where you want it. More importantly, when you can do that, you can make better decisions both professionally and personally. The future is a smarter place because we can extract value from the increasing volumes of data that used to be unmanageable, and as a result, we can make better decisions with information that is on demand, simple and easy to access, and predictably available when we need it. But just how much data are we talking about? According to the IDC Digital Universe study, by the year 2020, there will be 40 zettabytes of data. Another way to look at that is it would take 40 billion 1 terabyte drives to store all of that data. That is an enormous amount of data to be stored, managed, indexed, and otherwise understood so that we can extract both the personal, professional, and commercial value from it. Every enterprise has a huge amount of existing storage infrastructure. This is where the data that drives the business lives, and it is extremely important to keep it running so the company can function. However, maintenance of existing infrastructure can consume more than 3/4 of most IT budgets. This means the CIO has a hard limit when it comes to funding new applications that enable driving the business to new frontiers, to new opportunities, to new financial success. Is your organization's budget growing at double-digit rates? Probably not. At the same time, 86% of businesses believe all data has value. And yet 48% admit they're not storing all the data available to them, and yet all of them realize the need to preserve valuable data. If we look in the chart here, we see that the amount of data being created over the next several years will be that 40 zettabyte number by 2020. And there's a subset of that data that would be qualified as truly useful, not transitory, but things we'd want to hold on to or to be able to extract additional value from. But when you take a look at that in comparison with the projected shipment of storage capacity over these years, we see there's a huge deficit in the amount of storage being shipped to be able to handle the useful data out there, let alone all the data being created. So it's very clear there's an emerging need for new solutions or a new approach to data storage. Even within existing budgets, the IDC Digital Universe study shows there'll be twice as much useful data created as the ability to store it. But budgets aside, how will organizations deal with this massive growth in data? So with more data comes more challenges. Data growth continues at an alarming rate. It is simply unprecedented in the history of technology. Storage demand is far outstripping budgetary growth, and there doesn't seem to be anything that's going to slow down this demand. And yet we see that traditional storage solutions do not cost-effectively serve data at scale. What worked well at one capacity does not automatically scale to the capacity that today, let alone the future, will bring. Fortunately, object-based storage offers a cost-effective solution for storing data at scale. So let's take a look at object storage and see how it differs from traditional approaches to enterprise data storage. You've probably heard about object storage, but do you really know what it is? Object storage isn't a physical device. It's how we use physical devices, a logical construct of how we store data on media. But why are we doing this, you may ask? Haven't we solved our storage problems already? Let's take a look at the three most common networked storage approaches found in enterprise today. That's SAN, or Storage Area Networks, NAS, or Network Attached Storage, and S3, or what is commonly known as Object-Based Storage. SANs, or block-based storage, is very important in the data center, particularly for high-performance storage needs. You'll find transactional databases and other things where latency and the absolute fastest throughput are critical. Block works very well at delivering this, particularly in a RAID configuration, so as to provide some amount of protection against failure. However, block is a highly specialized approach. It does not have a lot of intelligence taking place at the storage level, and it relies on the applications to manage the storage. Some of the challenges with block-based storage is that it breaks down at large scale. In other words, it's very hard to build a large SAN that is both cost-effective and easy to maintain. Block-based systems are optimized for performance, but they do cost a lot of money. Management is typically very specialized. You have database administrators who spent years honing their chops on the ability to place data in just the right location on physical drives to deliver the maximum performance and avoid things such as data locality issues or other hotspots with the data. So you have very specialized management needs to take advantage of block-based storage, much like a pit crew on a Formula One car. Most implementations for block storage are in RAID configurations, and you cannot easily swap out components within a configuration as new technology becomes available. Hence, it's a very disruptive path to change out storage to the next generation technology in a block-based SAN environment. There are also limitations of what RAID-based configurations can offer. RAID has been a very dependable and, frankly, very indispensable technology in the data center for the past 25 years or so. However, we are reaching the limitations of what RAID can do and how well it does it, and it doesn't go to scale at the levels that we need today in the data center or the cloud. File-based solutions are a more intelligent implementation, if you will, over block. There are some trade-offs on them. However, they've been very popular inside enterprises in that they are relatively simple to use. A file-based access paradigm is pretty well understood by most of the clients in a commercial setting or a data center, such as a laptop or desktop computer or workstation. However, file-based implementations suffer from a similar scalability issue when you get to enterprise or cloud-level scalability. What works great on the desktop or a server of yesteryear doesn't meet the needs for scalability when we're talking about private clouds and public clouds, basically planetary scale. File systems do offer pretty good performance. File systems are somewhat less expensive than block-based implementations, but they don't have quite the same degree of performance. However, for many workloads, it's more than adequate. You do get simpler management in a file environment because you have the file system doing a lot of the work for you, and you're not having to have applications directly access physical sectors on a disk drive. However, if the implementation is based on a RAID configuration, you have the same disruptive path to next-generation technology as common in the block-based environment, because you are limited to the same capabilities of RAID-based disk implementations. Again, RAID was a great technology for what it was intended to do. Its problem is scalability in large enterprises or cloud-based implementations. Object storage provides a flat namespace, in other words, almost infinite scalability without the limitations of a file system or the delays involved in looking up data within a file system. It offers good performance for many workloads. It is certainly not a Formula One race car, but it is a more than peppy sedan or even station wagon, if you will. The cost of object storage is one place where it really shines. You're able to deliver much higher density and much higher capacity at a dramatically lower capital expense, but also at a lower operational expense because it has a much more simplified management structure. You manage for a namespace as opposed to managing for a RAID stripe. And as a result, there's far greater flexibility in how storage can be used within the data center, and is frankly much easier to manage, and that management can cross multiple data center boundaries. It also supports multi-generational storage. Since it is a scale-out model, it's possible to continue to add additional capacity or nodes of different eras of technology and have them still work within the namespace. So as a result, as you need to scale in an object environment, there are no technological disruptions to existing resources. You simply add with the new technology and grow out the total capacity available. And lastly, an object-based environment is RAID-free. Rather than using RAID to create data protection, you use erasure coding instead, which is a far more flexible solution that is not as dependent on the hardware for data protection or recovery of data. And this is an important distinction between object-based storage and other legacy approaches, and one we'll dive into next. It's important to keep in mind that data needs to be protected not only from data corruption from equipment or location outages, but also just from aging on the media, and this is especially true in large-scale deployments. The growth in modern hard drive capacity is unprecedented. Whereas a few years ago, a 400 megabyte drive would have been considered very dense and frankly a great storage value, the fact is today that 4 terabyte, 6, 8 terabyte drives are common, and 10 and 12 terabytes are actually increasingly the norm. The challenge with all that data density is that most data protection schemes today are based on the concept of a RAID configuration or a redundant array of independent disks. Under a RAID 6 implementation, you can lose up to 2 hard drives within the RAID set without suffering any data loss. When a disk becomes unavailable, the data can be rebuilt based upon the parity information that has been spread across the other drives. Because there is a trade-off for this in that it takes time to rebuild the data when it's lost from a physical drive. In a lightly loaded system, this might have a minimal impact on overall operations. But on systems with heavy read and write activity, in other words, the normal data center, the rebuild time can cause performance to suffer, especially if you're under very heavy loads. During this rebuild time, you are at risk of an additional error causing difficulty. The challenge that we face is that RAID rebuild times increase with hard disk drive density, and they can become an unmanageable liability. As noted in this chart, as the size of the disk drive increases, and the overall array size therefore increases, the likelihood of a rebuild operation failing due to a read or disk error grows dramatically as well. The challenge is that RAID protects your data only when it reads. If data is parked out on the drive and it isn't accessed for some amount of time and bit rot or other degradation of that sector, for example, takes place, a RAID implementation doesn't offer any protection against that. Bit rot happens when the block isn't read, and since RAID doesn't read the blocks until you ask for them, it's too late to know if there's been a failure, and that's what increasingly raises the risk of a RAID rebuild failure occurring because of bit rot or other inability to access data within the RAID group. The result is data loss. RAID is an equal opportunity failure risk for any vendor's high-capacity drives when deployed at scale. This leads us to the conclusion that the data center cannot support data at scale using 20-year-old technology. Another impediment to data at scale is that common file systems don't scale particularly well either. Gone are the days of 16-bit file systems with limitations of perhaps 64,000 files total. The challenge is still in the structural limitation of the systems. A modern 64-bit file system can easily scale over to 4 billion files on a volume, and this may sound massive by comparison with earlier limits. However, performance starts to suffer dramatically when the number of files in a folder starts to reach 10,000 or more. Adding more folders increases the complexity of a volume, and ultimately the issue becomes the time it takes to look up, locate, and assemble a file within a file system rather than the absolute number of files that can be supported on a given volume. The bottom line is that the performance and scalability of file systems decrease as the overall capacity increases. Well, combined in a world with ever-increasing drive density, the need for scalability and the number of files and folders being stored is paramount. So once again, we see another limitation to scale with legacy approaches. So the answer is rethinking data at scale. How can the enterprise, private cloud, or cloud support data at the scale that is needed for today's applications? Object-based storage offers us the opportunity to rethink data at scale. But object storage is about how data is stored on storage media, not the storage media itself. You can create an object store based on hard drives, flash drives, or for that matter, floppy disks. Object storage is a complementary third storage methodology for the data center. Object storage enables extreme scalability due to its flat architecture and its single namespace. With object storage, you can scale literally to the clouds, be they private, hybrid, or public. Object storage also has minimal impact on the data center should there be a read error or a drive failure. By virtue of its distributed erasure coding approach to data protection, replacing a failed drive does not require immediate action, nor is there a performance impact incurred solely due to a bad drive. With object stores, you can replace failed equipment when it's convenient. It doesn't have to be 2 a.m. on Sunday, it could be 10 a.m. on Thursday. You have a high degree of data protection available through object storage. This is enabled through the highly distributed nature of erasure-coded data. You also have a single namespace for simplified access, but also simplified management of objects. Whether your object store is in a single location or spread amongst multiple data centers' geographies, it still provides a simplified access and management paradigm for the enterprise. So let's take a closer look at how data protection can be delivered through an object store without the limitations of some current data protection approaches. In a RAID configuration, or specifically RAID 6 in this example, you have two additional disk drives in the RAID set that allows you to create parity information and spread it across several drives. As a result, you can incur a drive failure and still rebuild the data from the information available on the other disks in the set. It is very accurate to state that RAID protects disk drives. But for some of the reasons we had described earlier, RAID does not really protect data. Erasure code, on the other hand, is all about protecting data, and there is not a direct correlation to the hardware and the data being stored. Rather, there's distribution of data shards across several different media comprising the object store. Let's take a look at the flow of how your data is protected with erasure coding. First, the object is received. Next, a dynamic rateless erasure code is applied. The data is sharded into multiple segments and committed to several disks. Once a second object is received, erasure code is applied to the new data. Those data shards are then committed to potentially different disks. This allows protection against multiple concurrent failures. It also has the advantage that it eliminates hotspots, as data is distributed across available drives and they can be monitored for their level of utilization, capacity, and so forth. The result is that you have a highly resilient environment, and you can be protected against multiple read or outright drive failures and not lose access to the data. Also, in an erasure-coded environment, there isn't the concept of rebuilding a RAID group, which can take hours if not days. Rather, data is rehydrated on the fly. For example, in an environment which would be known as an erasure code of 18/5, this means there are 18 shards of data that comprise any given object. The first 13 returned by the system are sufficient to rehydrate the data. It does not matter which 13 are available or the order in which they come in, that is sufficient to rehydrate the object. Hence, up to 5 of the shards can be unavailable for any reason, and there's still no impact on the ability to retrieve the object. Unlike a RAID environment where the rebuild time can lower performance, the use of erasure code in rehydrating an object has very low impact in case of hardware or other access failures. You may be wondering what erasure coding actually is. Let's take a look at a simple example. Erasure coding takes original data and then encodes it in such a way and compartmentalizes it such that when we want to rehydrate the data, we only need a subset of the pieces to be able to recreate the original information. Well, let's consider a very simple example. If we have an original object that had a value of 75. Now, this isn't necessarily the number 75, but it's just a concept that we have a collection of data here with some value, and we can split it into components. So in this case, let's say our original value is 75. And then we can say that x is equal to 7 and y is equal to 5. And then we go through encoding. Well, this encoding process will create a series of equations. In this example, we're going to have a 3-1 erasure encoding. So we're going to have a total of 3 shards, and we only need 2 of them to be able to rehydrate the data. So in our encoding here, we end up with one equation that says x plus y equals 12. Well, if x is 7 and y is 5, 7 plus 5 is 12. Likewise, 7 minus 5 is 2, and 2 times 7, or 14, plus 5 equals 19. So we have 3 different equations here, and these 3 shards are written into the object store. Now, when we want to rehydrate that object, we just need any 2 of those 3 equations to be able to decode it. The way in which we do this is we solve for x. Now, I apologize to those of you who never wanted to see algebra again after you left high school or college, but here it is. If we take the 2 equations, x plus y equals 12, x minus y equals 2, and we add them together, we have 2x equals 14. Well, we solve for x, we get x is 7. But we could also get that out of using two of the other equations. 2x plus y plus the equation x minus y equals 2 yields 3x equals 21, divide out by 3, and again x equals 7. So now that we know what x is, we then solve for y. X is 7, therefore 7 plus y equals 12. We know that. Subtract 7 from both sides, we get y is 5. Or 7 minus y is 2. Remove 7 from both sides, we have minus y equals minus 5. We multiply that by negative 1, and we have y is 5. So we have x is 7, y is 5, and then we're able to rehydrate our original object and get 75. Now this is a very simple example, but the concept is the same. In an 18.5 erasure coding environment, that original object is sharded into 18 different equations. When we want to rehydrate, if we have 13 of those, we have enough to be able to decode out what the original values were and rehydrate our object. So it's much more complex, but the process is the same. So you see here, although we have 3 equations, we can get our original answer with only 2 of them. Just scale that out. If you have 18 equations, we only need 13 of them to be able to get the result. So that's how erasure encoding works. Well, erasure coding does an excellent job in protecting against data loss due to the inability to read a shard. Protecting the shards as they lie dormant on the disk is equally important. We need to build upon erasure coding in order to enhance data integrity overall. Remember, whereas RAID protects disks, object storage protects data. It does it through erasure coding, but it's equally important to ensure that bit rot does not degrade data when the shard is called upon to rehydrate the object. Data availability alone is not sufficient. Data durability is of equal importance. Bit rot happens when the block isn't read over time. Now, RAID doesn't read a block until you ask for it, and if bit rot has occurred, it's too late. If you take an approach such as that offered through Bit Dynamics, you do background testing for data integrity while the system has spare resources. Bit Dynamics extends erasure coding by proactively testing bits in the background to avoid read failures. If the sector can't be read, the data can be recovered by one of the other 17 shards and the sector marked bad on the disk. The replacement shard is written somewhere else, and life moves on. We can rehydrate the object at any time. This is in sharp contrast with a RAID environment, where if a read error occurs during a rebuild operation, data can be lost permanently. There's no protection against bit rot until it's too late. Ensuring data accessibility and resiliency is a paramount concern for any data center. Typically, sites will replicate or maintain multiple copies of data at multiple locations so that in case there is a power failure or a catastrophic event that takes a particular data center offline, there is a way to fail over and continue operations. One common approach to this is the replicated or multiple site approach. Say, for example, you have a major data center located in New York City. It is not uncommon to also have a replica or backup site located across the river in Jersey City, New Jersey, and perhaps a third one in upstate New York somewhere in Westchester County. With this 3 redundant site approach, if you do lose connectivity for whatever the reason to one of the sites, the other sites can take over and provide access to the data and applications. This approach does protect against an outage. However, it is very expensive as you need 3 copies of all of the data and essentially 3 copies of the data center in order to provide this accessibility in case of an outage. There are alternatives to strict replication, and one of those is a geo-spread approach using object-based storage. In a geo-spread environment, you have 3 locations, just like we did in the replication example. We have one upstate New York, one in Manhattan, and one across the river in Jersey City. But the difference is the resilience is not created by duplicating the hardware and the data stored within it. Instead, the resilience is a system attribute. It is part of the design of a geo-spread system. You have 3 portions of the object stored in 3 different locations, but it is not necessary to replicate all of the data to a total of 3 locations. Instead, 1/3 of the data is in each of the locations. As a result, you have less network traffic involved, and if you do experience an outage, your erasure encoding is such that you can still survive the loss of a particular sector or drive, controller, rack, or for that matter, an entire data center, because the erasure encoding ensures that you're able to rehydrate any object, even if you only have 2 of the 3 data centers available. One of the large advantages of this approach is that it offers the same degree of protection against a site outage. However, it does so at 48% less overhead. Rather than needing 300% of the data being stored, you need about 160% of the data stored across the sites. As a result, you have a more efficient and more cost-effective approach. It also helps somewhat indirectly in the case of load balancing or other considerations. In an 18.8 erasure-coded environment, you only need 10 of the shards to be able to rehydrate any object. It doesn't matter which 10, it's the first 10 that are available. If one site might be experiencing low connectivity with the others, or some other blockage that reduces performance, you can still rehydrate objects without concern. Likewise, as loads shift over time, it may be quicker to receive the 10 shards through some other combination of resources. The fact is, you can always rehydrate the object with 10 of the 18 shards. So with GeoSpread, you end up having a self-healing with no single point of failure approach of roughly half the overhead of a triple mirror. Now, if you take this one step further and are very, very diligent in how you lay out this data, of your 18 shards, you would make sure that only 6 of them are located in any one data center, and those 6 share no disk drives, or for that matter, shelves in the data center itself. As a result, with the highest spread of the data, or using bit spread technology, you're able to protect against performance limitations by running into hotspots or other data locality issues within the data center. So the combination of erasure coding with a very distributed approach to data location across 3 geos can give you very, very high data accessibility and resiliency at a substantially lower cost than the traditional triple mirror approach. Well, now that we spent some time with the theoretical examination of how object storage works, let's take a look at it in action. What are some of the practical use cases where object storage is delivering value into data centers today? One example is a service provider located in New Zealand. Rivera Cloud Services offers a variety of simple, cost-effective cloud services for the nation of New Zealand. Now, New Zealand, some folks may not realize, is located in an earthquake belt. So one of the key operational requirements is they had to be able to survive earthquakes, which dictated a distributed model for their solution. The company was also looking for a very cost-effective or low-cost implementation so they could be highly competitive in their marketplace. They also recognized with the continuing demand for data storage, they had to be able to dynamically scale over time to be able to add more capacity only when it is needed, so they did not have to absorb the overhead of deployed technology that's not generating revenue. It was also a requirement that they have strong consistency, that is, immediate consistency between data when it is written, so that any subsequent read, regardless of where the shard came from, always represented the most recently committed data. And they had need for several different applications as part of their business model. One was to be a simple cloud service, but more specifically to offer backup and archiving as a service, along with disaster recovery, and to be able to support big data applications. The view on the right of the screen is actually a screenshot from their website. And you see they tout a simple and cost-effective solution for as low as 6 New Zealand cents per gigabyte per month. Unlimited scaling, their vault is geared for deployments of all sizes starting in hundreds of terabytes up through exabytes to even zettabytes. And you'll also notice their web copy features the extreme efficiency that they have achieved by using a GeoSpread object store as opposed to traditional replicated approach. Object storage is a logical fit to meeting the at-scale needs in the cloud service provider space. Other places where you can find object storage in action includes media and entertainment. For example, the Montreux Jazz Festival has deployed a 3-geo spread solution that will allow them to digitize 50 years worth of audio and video assets from multiple variations of tape technology into a single active archive, which means that their video assets will always be available, the data durability and data preservation will be guaranteed, there will not be any more oxide flaking off of the tapes. Likewise, in motion picture studios and even pro sporting franchises, the use of object storage as a media content archive is very helpful. You'll find in studios that it is used in post-production, broadcast, and video on demand servers, and it also eliminates the mishandling of assets within the vaults. In broadcasting media transcoding and content delivery network origins, object storage plays a key role in making for massive scalability and density while providing high-performance transcoding targets for more than 15 of the most common digital formats and allows major broadcasters to undergo retranscoding as frequently as once a quarter. The reason for this is the standards and transcoding algorithms are changing and improving over time, and quite frequently major content distributors will want to recode their assets so as to always be taking advantage of the latest technological advances. Overall, we're noticing an increase in the quality of experience is driving rapid storage growth in the media and entertainment fields. The movement from standard DVD quality to high-definition television to 2K, 4K, and now even 8K are dramatically increasing the bit rates and the size of files necessary to support the highest quality media and entertainment assets. Object storage is a natural fit to meeting these at-scale requirements in the media and entertainment space. So we spent about a half an hour reviewing object storage, why we need it, how it uniquely can support data at scale to overcome the limitations of past approaches while delivering space-efficient data protection and resiliency, and we've looked at a few example use cases where it's a great fit to meeting the problems in the data center. So let's sum up what we've discussed. Legacy approaches, when deployed at scale, fall short of meeting the needs of the data center. File systems' performance start to decline rapidly as the overall number of items stored increases. As a result, file systems constrain cloud-level scalability and do not provide what is needed to deploy at scale in a cloud-driven world. Managing a RAID group or RAID stripe limits the flexibility in how data storage can be scaled across the enterprise. We end up with a silo even if it's part of a greater group that is limited by the hardware construct of the RAID group. Triple mirror replication is expensive and it has complex management requirements. And while well suited for high-performance, low-latency environments, this does not represent the bulk of data needs within the enterprise at cloud scale. As the density of hard disk drives continues to increase, the impact on RAID recovery is significant, either the amount of time it takes for a RAID rebuild to achieve, or the likelihood that a rebuild will fail due to bit rot or other data durability issues. A failed hard drive in a RAID group requires immediate replacement, which means the service-level agreements in force to support your storage need to be 24/7 by 365. Remember that RAID protects disk drives, not data. Current technology is not cost-effective in storing data at scale, especially for big data or other archival usages. Conversely, object-based storage has different attributes when deployed at scale. A single flat namespace enables cloud-level scalability. Managing a namespace allows a much wider reach and simplifies large-scale deployments. 3-geo spread configurations are less costly than replication, and they also deliver a low-impact recovery from site outages at roughly half the resource cost of a triple mirror implementation. Erasure coding does not have a recovery time in the case of access failures. Rehydration of objects takes place at roughly the same rate regardless of where the shards come from. When drives fail in an object store, you can replace them when it's convenient. You have a fail-in-place operational environment. Erasure coding is designed to protect data, one of the most significant differences between an object store and a RAID-based data solution. As you can see, object-based storage can cost-effectively overcome the scalability issues of legacy-based technologies. The HGST Active Archive system is an example of a fully integrated object-based storage solution. It is highly scalable, up to 35 petabytes raw and beyond. It supports a single site or 3 geospread implementation that is less expensive and more reliable than triple mirror replication. Utilizing rateless erasure coding as opposed to fountain or standard Reed-Solomon erasure coding, you can achieve even higher resilience for your data placed in the object store. BitSpread offers automatic optimal distribution of data across the available storage, so that all shards are distributed as widely and evenly across the storage resources. BitDynamics protects data integrity by deploying over 6,000 equations in the background to dramatically reduce bit rot and deliver 15 nines of durability for your data stored. Encryption at the bucket level allows you the flexibility to deliver enterprise-class protection while staying away from limitations such as drive-based encryption. This is ideal in supporting multi-tenant usage of an active archive. Strong consistency means that you will always have fresh data. All data must be written and delivered across the store before it is acknowledged, so that whenever you read data, you are ensured that you have the latest operational copy. And the overall simplicity of a fully integrated object-based storage solution makes it easy to install. You can be up in a matter of a couple hours while achieving a very low total cost of ownership. And with that, it's time to open up for questions.
Yes, thank you, Clay. We have a number of questions that came in, and we will try to answer as many as we can. First question, Clay, is that you discussed the shortcomings of RAID, but it's used in enterprises. Can you elaborate on why RAID is not appropriate?
RAID is a wonderful technology for what it was designed to do. The challenges I've discussed about RAID are not that RAID is bad, but it's being misused. With smaller sized disks, such as, say, under 4 terabytes, but certainly under 2 and less, the rebuild time for a RAID group is within an acceptable limit. And when you're trying to create high-performance storage, which is typically going to be block-based, or high-performance file, RAID really is the only way to get that kind of extreme performance that's necessary. The challenge is that RAID itself won't protect you against bit rot. You need to have other kinds of software running, maintaining the integrity of your RAID group so that if you do have a failure and you go into a rebuild, that you don't have a second failure due to bad data on the drive, which then causes your rebuild to fail. That's the challenge that I've been discussing throughout our presentation today. So RAID is not automatically bad, but using RAID at large scale in an archive type situation is fraught with difficulties. Using RAID for smaller size clusters of disks for high performance computing, it's the best technology we have for that end.
Thank you. That's a great point, and thank you for clarifying that. Another question that came in is you talked about object storage for cloud service providers and media and entertainment. What are some other ideal use cases for object storage?
Well, those are some of the low-hanging fruit, but another place where we've seen a lot of traction is in life sciences, in areas related to genomic sequencing or microscopy, or where you have very, very large amounts of data. Like today's electron microscopes can produce huge quantities of data out the back end. And digitizing of X-rays or other film-based media, once digitized in detail, become quite large in size. Genomic sequencing is an example of where there seems to be an unending amount of data involved when you run an entire human genome and sequence it out. That's another great use case for active archives. As a backup or archive target, object storage works very well because it's able to scale tremendously. And when you think about archives that are being held for best practices for months or years or even further, or even for large backups where data is huge in quantity, but the access might not necessarily be as frequent or continuous, this is another place where object storage allows you the economy of scale while still providing a warm access to data and information at much less cost than traditional primary storage or secondary backup or archive tiering solutions.
Thank you, Clay. Another question for you, Clay, is that you said in 3GEO spread configuration, you can lose one site and still operate. But isn't it true in a triple mirror replication, you could lose two sites and still be operating?
Yes, that's true, but let's think about that scenario. If you were to lose two data centers, wouldn't there be some other cataclysmic event taking place in the world around you? I mean, just think in the example I gave of New York City protected by New Jersey and lower upstate New York. If two of those regions were struck by severe outages, there is something going on, whether it is a man-made or a natural disaster. There's a lot more problems to be worried about at that point than, frankly, the data center. Now, that said, it is true. A 3GO will allow any one data center to go down. However, it also requires about half of the investment in storage that a triple mirror has. It also requires 2/3 less networking activity because you're only sending 1/3 of the data to each of the data centers. So rather than having 3 times the amount of capacity in order to store your data or having significantly higher network connectivity usage, you can get a single outage for roughly half of the investment and resources that you can in triple mirror. If a one-site outage is sufficient, I think for most organizations it would be, you can have that for roughly half of the investment. But frankly, I hope we would never be in a situation to where two data centers would go down, because again, something far more dramatic has occurred than just a simple operation of IT equipment.
You bring up a good point there, Clay. Well, unfortunately, that is all the time that we have for questions today. I want to thank everyone for attending live and on demand. If we didn't have a chance to answer your questions, we will be following up with you offline. And if there are any other questions that you do have, please don't hesitate to reach out to Clay. He's provided his contact information here. We'll also be following up with an email with some additional information and contact information as well if you'd like to get in touch with Western Digital. But I want to thank everyone again for attending, and until next time, make it a great day.